Hello again, everybody. Another video from day 2 types, this time talking about the substitution model of computation. So I referenced this in some of the other videos when we saw in the textbook that there's some examples in the text of how reduction works, and I just wanted to make sure that everything made sense by giving you some demos here on the virtual whiteboard, just so you could get to see them. So I've written down 3 functions that we're going to talk about, plus. Oh, no, in pen, please. Plus, in pen, please. Plus, mult, and minus. Okay, cool. So that's what we're going to take a look at. I've got a couple of examples I'd like to write down. So let's start with plus. The first example I'd like to look at is plus 2, 0. All right, now the model of computation, really only 2 things are going to happen in any computation in Coq and Galena programs. The first is substitution for function arguments. So this 2, right, this corresponds to n, the first argument, and this 0, that corresponds to m. While we're at it, I should mention that this 2, this is really equivalent to s of O. And this O, okay, well that's just O, 0, O, whatever, all the same. Great. So you plug those in. That means that this will immediately be equivalent to or equal to match, and then everywhere I see n, I'm going to write 2. Really, I'll write s of O, right? So this will turn into match s of O with O goes to m. Okay, but wait, what's m? M is 0. Or s of n prime. Now this is n prime. This is not n. It's a different variable. Goes to s of plus n prime, and then m, okay, that's going to be O again. Okay, all I did was I substituted what are called, these are the actual variables for the formal variables. I'll write those words down. These are the actuals, like the actual arguments you provide into the function, and these are the formals. Right? They're both arguments, not in the sense of dispute, but in the sense of thing given. But these are the ones we're actually providing, and these are just the names the function uses. Okay. Boop, 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 boop. You didn't think it was going to come with sound effects. Okay, so next we'll do the other rule of computation. So we substituted for a function. Now let's substitute in a match. So what we have here, this is the scrutiny of the match. And what we do is we just go top down looking at each case. Hey, is this the one? Is this the one? Which case do we want? Right? What's going on here? All right, so we can go through and we can say, okay, well, does it match this O, right? Does it match here? And the answer is no, it doesn't, because this has an S on the outside, so it's got to be this one. So that means what we'll get will be, well, what's n prime? N prime is going to be this thing. So this will be equal to S of plus S of O, O. Right, do you see where we got that? So that n prime got substituted in there because we found a matching branch in the match. Okay, so now what we have is we have this S lingering here, and then there's a recursive call here, so we need to keep going. But there's only these 2 rules of computation. There's only really 2 things that can happen, is we can apply functions and we can do matches. So, okay, we apply the function. Now this time, here, this will be n, and this will, it turns out, still be m. You'll notice in the function plus, m never changes. Okay, so we can keep going. So this s will sort of stay here on the outside. So we'll get s, and then we're going to get match S of O with, and then the body is the same, right? O, S of n prime, S plus n prime, O. Okay, so now we can look at it again, and we can say, okay, well, this S of O, what's it going to match against? And again, we're going to be in that second case, because there's an S at the front, so that means it's built with that constructor. Okay, so that means we're going to go into this case, and this O, this is going to be our n prime. So what we'll get is, well, the S stays from before. You don't want to forget this guy. He's got to come down. And then this sticks around too. We get that S. And now we have plus n prime O, where n prime was that O. So we'll have plus O, O. Okay, so now we're applying a function again. So we substitute. So S of match, right here is our n. So match O with, and I'll write it out just for completeness this time. For the others, I'll write it in a much more condensed form. O goes to M, which is here just, that, O. Otherwise, S of n prime goes to plus S plus n prime O. Okay, now this time, here's our scrutiny. Our scrutiny is just 0, the O constructor, and the first branch of the match, that matches exactly. So we'll go there. So that means we'll get oops, wrong color. It says it selects it, and then it doesn't really select it. S of S, and then what did we just return? What's there? Oh. Okay, that's 2. Let's scroll back up, or zoom back out. Plus 2, 0 is equal to 2. Hooray! Incredible. Okay, so that's how it works. I want to show 2 more examples for plus. Let's look at one. I'll write it a little more quickly and with a little bit less detail. So I might just say plus 0, 2. This will be a moderate amount of detail. It turns into match 0 with 0 goes to 2. S of n prime goes to S plus n prime 0. Okay, but we're in that case, so it just goes straight away to 2. I want to remark on the fact that the answers were the same, right? But we got very different computations. On the left-hand side, we had to go through a bunch of matches. 1, 2, 3 different matches. On the right-hand side, we went through just one. And you might be surprised to see this, but look, the way plus is defined is it looks at its first argument. So the bigger the first argument is, the more it's going to have to do. If you give it a small first argument, like 0, the smallest, it has nothing to do. It just returns its second argument. But if you give it a big one, it's going to have to step through every successor there to kind of paste it onto the other one. Okay, let's do one more. And I'm going to write it in a style that's sort of the one that I would like it to be cyan. Thank you. This is the style that I sort of use in my head. So what I'm going to do is I'm never going to write out a match. I'm always going to do the match part in my head. And I'm just going to sort of like see where we get every time. So let's see. Plus 3, 1. I'm also going to use Arabic Hindi numerals the whole time. You can, if you like, a great exercise is convert this to using successor and write it out carefully. If you do that, you'll know exactly what's going on. But this will be S of plus 2, 1. Ooh, that's terrible handwriting. That's the letter plus. Let me fix that up. Oy. Wow, who invited this guy? Okay, S of plus 2, 1. Well, that's going to be the same as S of plus 1, 1. Okay, well, that's going to be the same as S of plus 0, 1. Okay, but that's going to be the same as S of, well, 1. So that's 1, 2, 3 successors. That's going to be 4. 3 plus 1 is 4. Kindergartners, eat your heart out. Okay, let's do a couple more. Let's do some with mult. So let's look at the definition of mult again. Let's do mult 0, and I'm going to do something symbolic. Mult 0 Q. Okay, interesting. Well, that's fine. Q is a variable. I'm not specifying what it is. It should be some natural. That's cool. Let's see what happens. Let me write it out. I'll write out the match for this one. So this is going to be the same as, well, let's check it out. This is n. This is m in terms of matching the formals and the actuals. And apparently I've switched back to that. Thank you. You can see I copy-pasted it right out of the textbook. Who do I think I am? Okay, so now we'll match 0, because that's n, with, if it's 0, we'll just return 0. Otherwise, s of n prime plus q mult n prime q. Okay, but which branch are we in? We're in the first one. 0 is 0. So we'll just return 0. Interesting. Cool. I think it's kind of neat that we were able to do that computation without knowing anything about q. Right? We just told it in advance, look, it's really clear that this has to be 0, because just like, look at, we're going to do cases on the first n, and that's going to take us straight to 0. We never even look at the second argument. Okay, let's contrast that with mult q0. Okay, well, that's going to turn into pretty similar. Match q with, well, if it's 0, we'll return 0. Otherwise, if it's some s of n prime, now I'm not writing q prime because that's not the text of the program, even though n prime here will be 1 less than q if it matches. I'm going to stick with the text because I feel like that's what's honest. Plus 0 mult, oh, not q prime. You want it, but it's not true. N prime 0. Now at this point, we are, this is literally the technical term, we are stuck, right? Because look at this q. What is a poor q to do? We don't know what it is. If it's 0, we'll immediately return 0. But if it's not, we'll do something else. If you think about how this program runs, if q isn't 0, the answer will still be 0, right? After some number of steps, well, q steps, we'll get 0 because we're adding we're just adding 0 every time. That's correct. It's correct to say that this is 0 at the end, right? That is the right answer. However, computation alone isn't enough for us to see that. And again, just as we saw sort of an asymmetry in terms of how much computation happened in the concrete plus examples, here looking at these symbolic examples, we can see that, okay, something serious is going on in terms of what we can know from just running a program. This isn't super relevant to us yet. As we get into proof 4 weeks from now, 5 weeks from now, that'll be super, super relevant. For now, I just really want to observe that we can run programs that aren't complete, that are open is the technical term, that don't have all their variables filled in, but we won't always be able to get an answer. Okay, one last thing before I close this out. I want to do some examples with minus, just so that you get a sense of this pair match operation. So let's look at minus 3, 2. Okay, so this again, there's a couple of things worth noting here. First, up here, let me remove the mouse that is I'm nudging as I write. Up here, we have n and m written as just two arguments together, and then we do the pair match where we match on two things at once. So that's what I really want to highlight here is the way that's going to work. Okay, minus 3, 2. Okay, that's going to turn into highlighter equality symbols. That's going to turn into match 3, 2 with 0 blank goes to 0. S blank, because remember it's sort of that saturating thing. S blank 0 goes to 3. And S of n prime goes to minus n prime m prime. Okay, which branch are we going to be in? Well, 3, that's equal to S of S of S of O. And 2, that's equal to S of S of O. So the case we're in will be this last one. Right? They're both successors. So what we'll get out will be minus 2, 1. Right? 1 comes off of each of them. Now I wanna I want to note here that in plus and in mult, we had this thing kind of dangling off the end. We had this dangling plus in mult, or we had a dangling successor in plus. Whereas here in minus, we just return the recursive call immediately. You might worry like, oh no, like, are we going to keep doing recursive calls forever or something? Like, what's really happening here? But you'll notice that both numbers got smaller. And in any case, if cock accepted our program, it's going to terminate, I promise. Okay, if we keep going, this turns into match 2, 1 with 0 blank goes to 0. Scroll up, please. S blank 0 goes to 2. And S of n prime will go to minus n prime m prime. Okay, well, again, 2, that's S of O. 1, that's S of O. We're going to be in this last case again. Right here, we're right here. Okay, so that'll take us to minus 1, 0. All right, let's write out that last match we're going to get. So we're going to get match 1, 0 with, scroll up please, 0 blank goes to 0. S of blank 0, O goes to 1. And S of m prime goes to minus n prime m prime. Okay, but look, we have 0 in the second position. We're now in this branch. So we'll return this, which is the right answer. 3 minus 2 is 1. Okay, let's look at a couple more, and then we'll round it out. I want to do 2 more. I want to do minus 3, 3, and then I want to do minus 3, 4. I'll write them both out just so we have them. Here we'll do minus 3, 4, and here we'll do minus 3, 3. So I'm going to do this now in sort of the more like speedy style. So minus 3, 3, we're going to be in the SS case. So that'll take us to minus 2, 2. And then it's going to take us to minus 1, 1. And then it's going to take us to minus 0, 0. And then which case are we going to be in? Think about it for a second before you, I don't know before you what, but like think about it. All right, we're going to be in this first one, which you might think of as like the bad truncating case, but here it's actually being used to give us the right answer. Right? If the first number is 0, we're always going to return 0. But if the second number is also 0, we're not truncating. We're actually giving the right answer. Okay, let's look at minus 3, 4. You might already know what's going to happen here, but let's just go through the motions. We'll get to minus 2, 3. And then we'll get to minus 1, 2. And then we'll get to minus 0, 1. Okay, now we're going to be again in this case, but now it's really truncating, right? It's not giving us the right answer that you know from like the integers or whatever. It's giving you this sort of like truncated, like, it's 0, you know, caveat emptor. That's Latin for let the buyer beware. Like, look, if you're going to use our pred and minus functions, you should know this is what's going to happen. And like, you might not like it, but I can't think of a better definition. If you can, I'd love to hear about it on Zulip. There's definitely, this is just a convention. This is a choice. It is the choice we're going to make. So like, if you come up with something and you like it more, I'm going to tell you in advance we're not going to switch, right? Like later material depends on this definition. But I would love to hear it if you have other ideas about what this function should do. Okay, hopefully that was clarifying. You got some sense of how to run cock programs in your mind and on paper. It's a really useful ability. You can't write a program if you don't know how the program behaves. What's nice about these Galena programs, these programs in Coq's functional language, is that they're really simple. These are really the only 2 computation principles, function calls and matches, and that's really all that's going on. So once you get these, you know how a Galena program runs. Chickens, they're simple animals. All right, talk to y'all soon.